All right, hello everyone. This is the first video for section 2.1 from our textbook. As we go through this, you may see on Warm-Up that there is a classwork assignment related to section 2.1. Just so you know, the second part of this video that I'll give you tomorrow will be most useful for completing that classwork assignment. However, you can at least look at it after this and you might see kind of what to do. Okay, so when I describe calculus to folks, this is an analogy I always like to use, that all the math you've learned up to this point, so everything you learned through elementary school, middle school, high school, all of the algebra, the pre-calculus, all of those sorts of things, I like to think of that as the alphabet that you've been learning. And with calculus, what we're going to do is we're going to take that alphabet and start to make words with it. So I remember when I first learned calculus, I was just so amazed by the concepts. And it seemed to me that calculus was describing things about functions and graphs that had been in front of my face the entire time, but I just hadn't been able to see them until I got to this level of math. So I always really love teaching these things to other folks, and I'm really excited to be teaching this to you guys. Okay, so as we are talking about calculus, a big thing that we like to do, especially in Calc 1, is talk about finding the slope of tangent lines to graphs. And so we'll spend a lot of time doing that over the course of the quarter. But before we do that, we'll take a little bit to figure out how to do that, a few sections. We should first talk about the difference between a tangent line and a secant line. And I'm going to read some definitions for tangent line and secant line. Unfortunately, it's difficult for me to write them all the way out here. But I will draw some pictures that'll hopefully help you. So a tangent line, first of all, is a line that touches a curve at exactly one point without cutting it. Okay, so let me show you an example of that. So here, if I have a graph, say it looks something like this, and I choose a point on that graph. So say I use this one right here. Okay, well, a tangent line to that point, as the definition says, it's one that's going to touch it at exactly one point without cutting it. So this line here, this would be an example of a tangent line. So notice it touches the graph at just that single point, no other points, but does not cut through the graph. So let me show you what that would look like. So if we had a line that touched it at one point but just cut right through it, what that would look like at that same point, so if here's again is our point, would be something like this. And as you notice, the one that I've drawn here would actually touch the graph at more than one point. But the point is that it's cutting through the graph. So that is an example of something that is not a tangent line. Okay? Now we differentiate a tangent line from a secant line, and in that a secant line is a line that intersects two or more points on a curve. So in fact, that one that I just drew, that would be an example of a secant line because it would hit the graph at more than one point. If we use that same red point here, and want to draw a secant line through that, an example of something like that would be like this green line. So notice that it hits the graph at two different points, the red one and the green one. So that's an example of a secant line. Also, as the definition says, a secant line can hit at more than one point. So if you think about, say, like a sine or cosine wave, you can very easily draw a secant line here that is going to intersect the graph at an infinite number of points. All right, so that's tangent line versus secant line. On these next slides, I just have some more examples of that to help us visualize. So again, there on the left, you see the tangent line intersecting the graph at just a single point. and not cutting through it. And then there on the right-hand side, you see, again, the secant line, very similar to what I was just drawing, where it goes through the graph at 2 points. And something we're interested in is looking at the relationships between secant lines and tangent lines. So notice here, and this kind of relates to what I was just doing on the previous, or the drawings that I had, we have this point here. Oops, sorry about that. We have this point here, and they've drawn a tangent line through there. And they've also drawn a secant line that goes through the same point and another point on the graph. And what we are often, or as you might imagine, we can look and see what happens as we take this second point and move it back towards the first point. So that's something that we'll be interested in this section. So as an example of that, I have a nice animation from Desmos. Okay, so you notice here we've got a graph very similar to the one we were just looking at that has a tangent line and both the secant line. So notice the green line there is a tangent line, the blue one is a secant line. We have this point here that is going to be fixed, and we're going to look at what happens as we take this point here and slide it closer to that one. Okay, and I'm going to actually back it off a little bit so we can see it a little bit easier. Whoops. Okay, so if you notice, if I move that point back, right, you can really see that it's a secant line. Now as I move it forward, sorry, just 1 second. Okay, so as I slide that point forward, notice that the blue line, as the blue point gets closer and closer, the secant line is becoming closer and closer to a tangent line. Okay, until they're right on top of one another, then it is a tangent line. Okay, and so that is kind of the relationship we see. Is if we have a secant line, we move those 2 points closer and closer together, and we get a tangent line. And we can also do that from the other side. So if I move the blue point forward here, notice, again, we have a secant line, although it's a little harder to see. If I back it up now, and as it gets closer and closer to that orange point, then it becomes a tangent line. And so the reason this is helpful for us, so this idea is helpful for us, is because, like I said earlier, we're interested in often finding the slopes of tangent lines, and secant lines are one thing that can help us to try to estimate the slope of a tangent line. Okay, so let's look at how that might work. So look at a function f of x equals negative x squared plus 5, which is a function that looks fairly similar to the one we were just looking at. When we look at the coordinate 1, 4, that's going to be the point P in what we'll be looking at here. Okay, and we want to find the slope of the secant line between P and each of the points on the curve at each of the following values of x. So just an example or a visualization of what's going on here is we know the graph of negative x squared plus 5 would look something like this. The point 1, 4 would say be somewhere like right here. That would be our point 1, 4. And what we're going to do is look at points with other values of x. So like say x equals 2, which would be here. Okay, so the point with 2 as the input. And we'll think of there being a secant line between those 2 points. And we want to know what that slope is, and then we're going to take that second point there, and we're going to move it back so it gets closer and closer to 1. And also I just realized, no, that's correct. Okay. All right, so using this first one with the x equals 2, so we need to find the slope between these 2 points. And if you recall, our slope formula is m equals y2 minus y1 over our x2 minus our x1. Okay, so when you do that between these 2 points, now obviously in order to do this, we also need to know our outputs. When we do an input of 2, so we know our output right here. And so to do that, we just take the value 2, plug it into the function up there. So we have f of 2, which will give us the negative of 2 squared plus 5, which if we work that out, that will give us a positive 1. So now we can take those, so we know that that's the output here. Take that along with the other point, plug them into the slope formula here. So remember, it doesn't matter what our y2 and our y1 are as long as we're consistent. So I'm going to call this one here y2, so this is x2, so this will be y1 and x1. So our calculation here will look like 4 minus 1 over 1 minus 2. And so we'll get 3 over negative 1, so we get negative 3 here. So it looks like our slope of our secant line there would be negative 3. All right, so I'm going to clear this up a little bit. Put in that we knew that this point here was 2, 1, and then we ended up with a slope of m equals negative 3. Okay. When we go through and do this for the rest of these points, so for x equals 1.5, x equals 1.1, x equals 1.01, and notice as we go along, those input values there are getting closer and closer to 1. So our slope of our secant line should be getting closer and closer to the slope of the tangent line. Now, I'm not going to go through all of those step by step, but I will tell you what the points should be here. So this one should be 1.5, comma, 2.75. Okay, and when we find the slope here, the slope we end up getting is negative 2.5. Okay, for the point 1.1, or when x equals 1.1, the point we get is 1.1, comma, 3.79. Okay, and we plug that into our slope formula. Then we get m equals negative 2.1. And then finally, we have the point 1.01, comma, 3.9799. And there we'll get the slope of negative 2.01. Okay, and if you look at that, look at the progressions of the slopes. So we had negative 3, negative 2.5, negative 2.1, negative 2.01. As we're moving the values of x closer and closer to 1. So for the last part of the question here, we're asked to estimate the slope of the tangent line. Based on what we see here, it looks like those values are getting closer and closer to negative 2. So we would estimate that the slope of the tangent line here is negative 2. All right, now one more thing I want to show you guys here is you notice that in order to do this, you had to evaluate the function several different times at different values. And so on your calculators, not what I'm looking for, this, trying to pull up this, there we go. On your calculators, you can use some of the features here to help you evaluate these functions fairly quickly. So the function we had was negative x squared plus 5, and I had to plug in different values for x. So one way we can do that on our calculators is use the store function. So if I do say 1.5, this little STO with the arrow here, if I press that, x, what that will do is store the value of 1.5 as x. So in my calculator, I can do negative of x squared plus 5. And again, the calculator will evaluate it at the value of 1.5, which gets the 2.75 that I had before. When you have to evaluate other numbers then, like say the 1.1, all you have to do is press 1.1 store x plus enter. And then if you hit second and enter, notice that right above it there's this word entry, and what it'll do is recall previous entry. So if I press it once, it takes me back to the thing I just put in. If I do it again, it'll take me back to what I had before. And now when I press enter, it evaluates that at the value of x is 1.1. We get that 3.79. So that's a way to save yourself a little bit of time. So as these functions perhaps get a little bit more complicated, you don't have to enter them all in all the time. Or re-enter the function every time when you need to evaluate it at a different value. All right, that's it for now. Thank you guys so much for watching.